I'll collect. Did anybody finish the report on that? No, I'll collect the reports at a later date. But you're looking for those favorable ion combinations, so it asks you to pick a cation and pick an anion. Or what happened. Today we're going to be looking at some other types of reactions. One type that's discussed in the book is a combination type reaction, but I don't really call it a combination. I divide chemical reactions into three types. What are the three types of reactions? Acid-base is one, redox and metathesis. Yeah. And so we'll be looking at that here. And so when they say combination reactions, I look, is it an acid-base, is it a redox, or is it metathesis? And so let's take a look at the first reaction here. The first reaction is we're going to hold a piece of magnesium ribbon at one end with crucible tongs and ignite the other using a laboratory burner. So this is just solid magnesium, and then we're going to burn it. And so when we burn it, what do we burn it in? Air. And what in air reacts with the magnesium? Oxygen. Oxygen's a gas. This is a combination reaction that's redox. It's an element plus element redox reaction. Redox, there's an oxidizer and there's a reducer. The oxidizer does what in redox reactions? Takes electrons. So which one is the oxidizer here? Oxygen. The oxidizers, when we look at the periodic table, occur on the left side or the right side of the periodic table? On the right side. So oxygen, whatever is further to the right end of the periodic table should be the oxidizer. Whatever is further to the left, it should be the reducer. So on the periodic table, that's left. And so we can predict what's going to happen. Magnesium loses how many electrons? Reducers lose electrons, oxidizers take. And so magnesium is going to lose how many? Two. Oxygen is going to gain how many? Well, each oxygen atom gains 2. So we have O2 minus. And so what we should form here is magnesium oxide, MgO. MgO is a solid. O2 is a gas. It looks like to balance this, we'll need 1/2 O2. Or we could just double everything. We go 2 magnesium solids plus an O2 gas yields 2 MgO solids. So this is the formation of 1 mole of magnesium oxide. This would be the formation of 2 moles of magnesium oxide, according to the equation, the ratios that we need. So, excuse me, this is an element plus element redox. And so it's a combination there. So let me go ahead and do that. We can combust some magnesium. Okay, magnesium is a metal, pretty lightweight metal. It has a gray appearance like that. And then to help get this ignited, I'm going to just ignite it in the Bunsen burner. I'm not going to hold the metal with my fingers. Just hold them using some tongs here. So, all right, you don't want to look at this directly because it's going to give off some bright light, actually. And I'm going to save the ash that's generated here. Probably should throw on my goggles in case. Okay, so I'm going to ignite this. It's going to be pretty bright. Got to disperse the smoke that's generated here, otherwise the fire alarm's going to go off. Actually, that didn't ignite all of it. Let me ignite the rest of it here. A little bit left. There. Well, maybe it did. I guess it did ignite all of it. Okay, let's throw that here. So the first part of this is demo. I got to keep track of who's here. So who just walked in? Okay, Jay and Giselle. Okay. So there's a residue, a solid kind of white residue. I had a little bit of water in here, but the solid white residue looks like this. It's coating the tongs. Look at the crucible tongs. They've got a white coating on there. And so that was the smoke that was generated there. Okay, the next part of this says to catch the ash and put it into a watch glass. We did here, and then crush it. Okay, so what I'm going to do is I'm going to do two things. I'm going to just get some water here and mix the ash, that is the magnesium oxide, with the water. Now, magnesium oxide, is it soluble in water? No, it turns out that oxides are insoluble, except for group 1 and ammonium. And so I'll try to crush it up here and see if I can get some to dissolve. But it doesn't really dissolve. It's going to make just a slurry or paste. Okay, so that's crushed up. And then I'm supposed to test the resulting mixture with both red and blue litmus paper. So I have some litmus paper here. Oops. This is the blue litmus paper. And then I have some red litmus paper as well. Let me get the red.
Red is for acids, right?
Yeah, red is for acids, blue is for bases. Well, the color. But the litmus paper itself, it goes like this. Bases turn litmus blue. Acids turn litmus red. And so if I have blue litmus paper like this, and I put base on this, it stays blue. And so what I'll do is I'm just going to take some litmus. I'm not going to dip the litmus inside the liquid because that will contaminate it. Litmus contains dyes, and I don't want the dyes to contaminate this mixture. So what I'll do is I'll get the stir rod, get some drops of solution, and then test it on the litmus like this. And take a look. And so when I look at this, the blue stayed blue. Nothing changed. But that doesn't mean it's an acid. What I'm going to do is I'm going to take some red litmus paper, and with the red litmus paper, I expect red litmus paper to turn blue if there's base. That's what litmus paper just tests if it's acid or base. So this is the red litmus paper here, and so let's see what color drops of this liquid turn it. Do you see much change? In color? No. There isn't much change in color. And so if it's like water, it's really not really acidic nor basic, then color doesn't really change one way or the other. And in this case, the color really didn't change. And so I'll have that. All right, there's one other thing. We add, and that would be phenolphthalein. Phenolphthalein also tests if it's acid or base as well. And the way phenolphthalein works is by changing color. Let's see. Phenolphthalein. This is the phenolphthalein. It's an indicator too. Phenolphthalein is colorless if it's acid, and it turns pink or purple if it's base. And so if I add a drop of phenolphthalein to this, what happens? Put a drop of phenolphthalein in there. Do you see what happened? The color did change. We have this kind of pink color now, which indicates that it is base or acid. Yeah, base. Bases turn it pink. Acids leave it colorless. So here, let me put some background on this so you can see it a little bit better. And so it turns out the litmus paper wasn't sensitive enough because the red litmus should have turned what color? Blue. But if it's not basic enough, then we may not notice it. Whereas the phenolphthalein is a little more sensitive, maybe a lot more sensitive in this case. And so what I'll do is sometimes these reactions are sluggish because magnesium oxide is pretty insoluble. And so let's see what we got here. Still really doesn't turn it blue. Can't see it. Putting some more on there. But it's definitely on the basic end of things here. And that's because of this. Magnesium oxide contains magnesium ions and oxide ions. But what do you know about oxide? Can you tell me one chemical property of oxide? What do you know about oxide, O2 minus? You remember anything from yesterday about O2 minus? Yeah, that's a physical property of oxide. That's good. So, oxide, magnesium oxide is not soluble. You can see it. It forms this crystals don't really dissolve. But if something's not soluble, does that mean it's 100% insoluble? No, a tiny. What do we mean by not soluble? We mean that less than. Anybody remember the number? Yeah. Less than 0.1 moles dissolves per liter. And so maybe a tiny bit does dissolve. But what chemical property of oxide do you know? Do you recall hearing about oxide yesterday? You recall something about oxide yesterday? Nothing? Okay.
Oxidation occurs when one electron is given to another and it's reacted.
Yeah, for redox. But I'm not talking about oxidation, which oxygen is the prototypical, it's why we call oxidation because of oxygen. Oxygen is a ubiquitous oxidizing agent, all around us. But right now I'm talking about oxide. There's a difference between oxygen and oxide. Oxygen is lacking the electrons. Oxygen wants 2 electrons. Oxide already has them. So oxide's happy as is. When we're talking about oxidizing agents, oxygen is a great oxidizing agent, oxide isn't. Oxide's a pretty poor oxidizing agent. Very poor oxidizing agent. Why? Because it already has 2 electrons and that's all it wants. It's got what it wants. So it doesn't try to get more. And so we can talk about the redox properties of oxide, but it wasn't the redox properties that I was mentioning yesterday about oxide. What was I mentioning yesterday about oxide? Doesn't kind of ring a bell at all? Just one chemical property of oxide. Just tell me one chemical property. So we talked about redox, but that's not the chemical property I'm interested in for oxide. Not really, not the toxicity. Oxide, a lot of people don't worry about. If your frying pan is a little bit rusty, well, yeah, I'll get to you in just a second, Samuel. But if your frying pan is rusty, do you worry about rust getting into your food? Is rust especially toxic? Iron 3 oxide? People don't even care, In fact, if you go, lattice is extremely strong. Extremely strong. But the chemical property I'm looking at is it's basic. Not only is it basic, it's a strong base. It's one of the few strong bases that you need to know. Oxide. And so, what do acids do? What do bases do? Acids have H+. Bases take the H+. And so, basically, bases take H+ from acids. And so, what happens is, most of the oxide is locked in the lattice here. So when I think about magnesium oxide, I don't think necessarily powerful base, because the oxide, and this stuff is pretty insoluble, right? But it's not 100% insoluble. A tiny bit does dissolve. If a tiny bit does dissolve, what happens to the oxide? The oxides are free from the lattice, and they can do what? What can they do? They can react. And so if the oxides react, they're going to react as bases, and they're very powerful bases. In fact, the strong bases are all similar. There's something called the leveling effect of strong bases, because all strong bases do what to water? Bases Ionized water or bases hydrolyzed water? Hydrolyzed water completely. And so what oxide does is it hydrolyzes water. In other words, it's going to attack water and take a H plus from water. If it takes an H plus from water, then we're left with OH minus. OH minus is called hydroxide, and then the H plus is lost by water. If the H plus is lost by water, then we're left with hydroxide. So we form two hydroxides. And so what happens is the magnesium oxide can react with a little bit of water. I mean, not much, because very little, if you look at that, very little magnesium oxide actually dissolved. You can see chunks of magnesium oxide still there. And it really didn't make an impact on the litmus, but we did see it with the phenolphthalein, which is quite a bit more sensitive. So the magnesium oxide plus the water gives us magnesium hydroxide. Now, magnesium hydroxide, is it very soluble in itself? No, because hydroxides are all insoluble except for which ones? Hydroxides are insoluble except for group 1, ammonium, calcium, strontium, and barium. So magnesium hydroxide turns out to be an insoluble hydroxide. It's a solid, so it's not very reactive in itself either. This reaction doesn't happen to a large extent, so I'm going to write the double arrows here indicating that it's only partial reaction, not a complete reaction. Whereas this would be a complete reaction. Whatever oxide is generated off the surface of the magnesium oxide is going to react with water to produce hydroxide. And so this is the reaction that we see. Magnesium oxide reacts with water to form magnesium hydroxide. That is, when the oxides break off, oxides are strong bases. However, magnesium oxide itself is not considered a strong base. Why? Because it's insoluble. Insoluble. All right, if we look at this combination reaction, you know, we're combining two things to form one. So we're combining magnesium oxide with water to form magnesium hydroxide. Does this reaction resemble the previous reaction at all?
Magnesium oxide.
Not really, because this reaction is what we call a redox reaction. This reaction is an acid-base reaction. But both reactions are combination reactions. So this is why I don't like the combination type, because not all combination reactions are the same. All acid-base reactions are the same, all redox reactions are the same, but not all combinations. So I don't like that categorization scheme. You could have different types of combination reactions which are totally unrelated to each other than the sense that you have an A plus B yields a C. Number 3, add a small amount of calcium oxide to a few milliliters of distilled. We don't have distilled water. You know, it says distilled water. Do you know what we have? We have industrial water, which is like tap water. This is tap water. We have this one on the left. Do you know what this is called? This is not distilled water. This is deionized water. Distillation is a very specific process where you boil the water and then you collect it. We don't boil our water. We just deionize it. This is deionized water. So I'm going to take some calcium oxide and add some water to it. See what happens. Okay, my computer is about to restart. Okay, for this particular reaction, it doesn't really matter if I add the water or if I add the calcium oxide. So what I'm going to do for this reaction is I have some deionized water in the wash bottle. I'll just put some deionized water in a test tube like this. I have some calcium oxide here. It's just this white solid calcium oxide. This has a flat lid, so I can set the lid down. I have a scoop here. I'm going to use this scoop to scoop some calcium oxide out of here. I'm just going to dump it in here. Is calcium oxide soluble in water? No. Not expecting. What I'm going to do though is I'm going to mix. You can mix by tapping it. But in this case, what I'm going to do is I'm going to try to dissolve as much calcium oxide as possible in the water. And so I just use this for my magnesium oxide. So what I'm going to do is wash it off. If there's still residue stuck on there, I'll use soap and water to wash it off. And then give it a final rinse with DI water. In this case, I'm just going to rinse with DI water. So I'm going to stir this up. It's not very soluble. In fact, calcium oxide we'd say is insoluble. Most of it doesn't dissolve. And so what I'm going to do now is I'm going to just test it with some litmus paper. That piece fell down there. So let me rinse off the watch glass here. It wasn't so clean before. All right, to this watch glass, I'm going to put a piece of red litmus and a piece of blue litmus. So red litmus. Here's my blue litmus. All right, so let's see what happens to let's see what happens to the blue litmus first. What do you think is going to happen? Well, calcium oxide contains the strong base what? Calcium oxide contains the strong base oxide, but calcium oxide in itself really isn't considered a strong base because it is soluble? Insoluble, because it's insoluble. So that strong base oxide is locked in a solid lattice. Can't really react freely. But anyway, let's see if some escaped, if enough escaped. If oxide escapes from the lattice, then it will attack water. All strong bases attack water to produce hydroxide. And so what should happen? Base should turn blue. What? Base should turn blue litmus blue. And so blue litmus goes blue. Do you see any change in the color? No. So blue stays blue. Base should turn red litmus. What color? Blue. I have solid white calcium oxide there. So, okay. So do you see that? Yeah. And so this is a lot more basic than the magnesium oxide. So this must be a little more soluble than the magnesium oxide, but both are insoluble. And so the same thing happens here. In fact, with the phenolphthalein, what's going to happen to the color? If I add a drop of phenolphthalein is colorless and acid, but pink and blue. So this should turn pink. So I'm just going to add one drop of phenolphthalein. Do you see what that is? Okay. That's it. So what's happening here is this. We have our calcium oxide. In this case, we're starting with just calcium oxide. solid, and we're going to try to dissolve it in water. It doesn't dissolve much, but the tiny bit that does dissolve will react. The oxide is going to attack the water to form hydroxide. And so what we're going to end up with is the formation of calcium hydroxide. Calcium hydroxide, is it soluble or insoluble? So hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, and barium. Have you guys started memorizing these? Are you going to have them down by next week? Next week is the test. Thursday. So you have another week. Get those. And so calcium hydroxide is aqueous.
Are you gonna go switch it again?
Yeah. All right, this is not. It's about to restart here.